Hey everybody, Mr. Morandi here again, and I want to walk you through our first slideshow in our third unit on energy, and specifically energy transfers and where we get our energy from. So let's get going. Today our topic is what is energy, and let's change it up because energy is all about change. This is actually one of the most fascinating units I think I teach in everything that we look at because it really gets to the crux of who we are as a species and why we're here. And I think that's huge. So energy is the cause of all physical changes in the world. Um, it's So all stuff in the universe is made of mass or energy. It's one or the other. And we've got some ideas about dark mass and dark energy and dark matter, but we're not really positive about most of that stuff. But we are sure about mass and energy. If you're mass, then you're a thing. This bottle of paint has mass. The heat coming out of my heater over here, my space heater, is just energy. It's just thermal energy. So you have to be one or the other. You're either made of atoms or you're made of energy. So energy is the cause of all physical changes to that matter, such as changes in the speed the thing is moving, or the height that it's at relative to the Earth's surface, or the temperature of that item, or its chemical composition even. I've got some pictures here. This is some electrical energy and a plasma in this globe. You might have played with these before. You put your hand on it and the energy reaches to your fingers. And this is an infographic of the electromagnetic spectrum. And that includes all light and X-rays. And we're going to talk about this in a little bit. But it's a good image to have in mind because further down the road, we will talk a lot more about the EM spectrum. But for now, energy is the cause of all physical changes. And it gets passed between objects the same way that money gets exchanged between people. You know, you give money to people for goods or services, and they give you money for goods or services, and we pass this money back and forth. Energy can be looked at kind of the same way because energy gets passed from one object to another. So if we kind of think about it in this terms of like a balance sheet, right? This 1 kilogram aluminum block at rest on the floor. Remember, at rest means it's not moving and it's sitting on the floor, so we can count its height as 0. And it weighs 1 kilogram. It's just a block of metal, and it has 0 joules of energy. For the people out there that are telling I'm wrong, there is a non-truth there, is that it does have energy locked up inside of it, but it's not energy we can easily access. So for now, for our purposes, we can call it 0 joules of energy. We say this block has no usable energy here. It has 0 joules of energy. If I want to lift it up 1 meter in the air, I have to apply some energy to it. In this case, 9.8 joules. Now you might recognize that number 9.8. That is also the acceleration of gravity on Earth, which is the nice part of the metric system. It's very easy to transfer from one unit to another, from one kind of thing like acceleration to joules of energy, because they're all very easily relatable. So moving this block up 1 meter in the air requires 9.8 joules. Now that energy has to be spent from another system, probably from my body, because I'm going to be the one picking it up and lifting it into the air. And now I'm going to increase the speed of this thing to 2 meters per second. I have to accelerate it. In order to do that, I have to provide it with some more energy. So I'm going to pick up this thing, and then I'm going to move it at a constant rate of speed. All of that requires energy that I have to put into the bottle, and that now raises its total balance to 11.8 joules of energy. I want to drop it back down a meter. Well, now I have to take the energy that's in that item and use it, and it's going to move down. Maybe I'll let it go and it will fall. And so when it lands, it'll expend some energy getting there. If I want to heat it up and expose it to some flames, well, now I have to give it 4.5 joules of energy to raise its temperature by 5 degrees Celsius. So all of these things are like money being exchanged, except that it's energy. You know, where did this flame come from? What's burning that's allowing the energy to be released and transferred to this aluminum block? Every physical change involves exchanges of energy, and the amount of energy determines the amount of change. If I was to take this and just kind of toss it in the air, I'm only giving it a little bit of energy, so its motion is only moving. But if I throw this thing into the air, it's going to go a lot higher because I gave it a lot more energy, right? I've got a space heater over here. If I leave it on low, it only heats up a little bit. But if I crank up the heat, it burns a lot more fuel, and it gets a lot warmer. And that leads me to the conservation of energy. This is one of those fascinating parts about this, is that energy is conserved. And what that means is, if you've heard of like conserving the environment, or conserving fuel, or conserving anything, it just means that it's got to be saved. Energy is always saved. There can never be new energy created. It can only be gained from another system. If I want to throw this in the air, I have to add energy that's coming from me. If I want to heat it up, I have to take energy from one source and add it to this object. I can't just create new energy to make it burn. And it can never be lost, right? If I was to throw this right against the wall, it's going to hit the wall and it's going to break a little bit of the wall. Not much, but just a little bit. Maybe it'll knock some dust off of the mortar on the wall. Or if you ever slap your cheek, you're pushing your skin. You're taking the energy from this place and putting it over here, and it's moving that object. So the energy has to come from one system and go to another one. Do you want to heat something up? Do you want to pick it up? Do you want to change the shape of an object or make any kind of physical changes of any kind? That energy has to come from somewhere. So the conservation of energy means, and this is one of the most important definitions you should remember this year, is that energy can never be created or destroyed. It can only be exchanged from one source to another. So that means I've got this propane heater over here, right? And there's a propane tank in it, and it's burning off fuel. That means that the heat, the energy in it, is not being destroyed when I burn it. It's becoming thermal energy and warming the air around me. That air is now going to dissipate throughout my entire basement / office, and it's going to warm up the whole room. And then when this room gets warm enough, that heat is going to go through the roof and into my living room, and it's going to warm up my living room. Now, that would take a lot of energy, right? I would go through this tank and a couple more before I started heating up my whole house, and I'd probably pass out from a lack of oxygen. So, not going to do that. But that energy isn't destroyed. Once it goes through my walls and up into the roof and into the living room, it would then pass out into the rest of the air in the world, and it would start to heat the world up. Again, not by much, right? But it would go somewhere. It wouldn't just go away. The room doesn't just get cold because the energy disappeared. The room got cold because the energy left to join another system out beyond the walls of my house. The energy can never be created, and it can never be destroyed. It can only go from one source to another. But that's the cool part, because there's a lot of energy in me. That means that all the energy in the entire universe was there at the moment of the Big Bang. It was never lost any energy, and it's never gained any energy. It's always been the same amount. It's just been passed between atoms and molecules. Now, that means there's energy that binds the molecules of my body together. There's energy that keeps the atoms together. The protons and neutrons and the nucleuses of the atoms are all bound together inside my body. The electrical signaling that goes on in my brain, where I have two little synapses and they pass charges between them, little electric shocks that create my thoughts and my actions and my ideas and the things that make me who I am. That's energy that was there at the time of the Big Bang. And 14 billion years later, here it is, making a web screencast of my lesson in the basement of my house in Rhode Island. That's amazing to me. When I die and my body goes into the ground, the energy that holds my atoms together gets recycled back into the soil. and gets absorbed by the trees and by the bugs and the insects. And they take that energy and they use it to create new cells and to move their bodies across the ground and to grow leaves to produce oxygen that other people will breathe. All that energy is still part of the world. It doesn't go away. To me, that's the most phenomenal piece of information I can give you all year. The energy that literally makes up my body was here at the Big Bang during that massive acceleration that started everything around us. It's phenomenal. But now, back to the stuff that matters for class. Energy comes in many types. We're going to go over these 7 kinds of energy in class this year. So I'm going to buzz through these fairly quickly, so you can always feel free to pause or go back or use this as a sort of like a reference. The first one is mechanical energy, and that's going to be the energy associated with motion and position. And that would include things like kinetic energy, like pushing an object or moving an object, or stored gravitational potential energy. When you lift an object up, it now has gravitational energy. I could let it go, gravity would pull it down, and it would land on something. If it was heavy enough, you could imagine it might break my toe, right? And so here I have a giant rock, right? If I was to drop this rock, it would land on my toe and break my foot. That's work. It's transferring that gravitational energy into breaking the bones in my foot. Or elastic potential energy. I grew up with 3 brothers, and I've been shot by a lot of rubber bands. Anyone out there with siblings knows your siblings will shoot you with a rubber band given the chance. That is when you take an object and you stretch it, and now it's going to want to bounce back to its normal shape. That's elastic potential energy. Radiant energy includes all forms of that electromagnetic spectrum that I was talking about before. And that includes things like the visible light that we can see. The actual image of me on your screen coming at you right now is radiant energy. It's light being broadcast at you from your monitor. But there's also infrared radiation. There's ultraviolet light, like the sun rays that burn your skin when you're outside in the summer lounging on our beautiful beaches. Microwaves, very small, high energy wavelengths of light that permeate into my Hot Pocket and heat up the water inside of it to make it a delicious snack of pepperoni and cheese and God knows what else they jam in that fake bread crust. The radio waves that travel across the landscape. These things can be huge radio waves, and transform that into sound in my car that I can listen to some music. Or even X-rays, very, very fine rays of energy that are so tiny that they can fit between my skin cells and bounce off my bones. That's all radiant energy. Nuclear energy, you can think the nucleus. It comes from the forces that hold the nucleus of an atom together. All those protons and neutrons jam together in the middle of an atom. If you are unsure what I'm talking about, maybe you've seen Jimmy Neutron, and he's got that symbol that shows up in between the slides. That's an atom, and you can see nuclear energy is the energy that holds that thing together. There's a ton of energy in there. It's the kind of energy source for the stars and our sun, which burns at 20 million degrees or something in its core. So very, very high energy. And when nuclear weapons have been used, they've only been used twice, and it's worth it to remember they were both times used by us on civilian targets in Japan. I think that's relevant to remember. The bomb that blew up Hiroshima was only 11% successful. The other 89% of the bomb didn't go off. And that little bit of the bomb that did blow up was enough to level an entire city in a moment. So there's a tremendous amount of energy there. And then electrical energy is energy carried in electrical currents. It's clean by nature, although the electricity that we get by burning fossil fuels mostly. So it's very dirty at production. But electrical energy in its own right is pretty clean. It moves through wires very easily, and it's a key energy resource. I mean, we'd be pretty bad off without electricity at this point. Your cell phone would stop working. You wouldn't be able to watch TikTok anymore. And you wouldn't be able to get these great science lessons delivered to you in your home from my basement. I would have to stand on the front porch and just yell really loud. That would be less effective. Unfortunately, all the electrical energy we have has to be derived from other forms of energy, and that's going to be the next lesson that we talk about. So chemical energy is the energy stored in the bonds between atoms. If nuclear energy holds one atom together, chemical energy is the energy stored in between those two atoms. So for instance, a sugar molecule is 6 carbon and 12 hydrogen and 6 oxygen, all bound together. You may have even made marbles into big long chains of molecules with little sticks holding them together. Those little sticks represent energy that hold those atoms together. And if I break that sugar molecule apart, I can use that energy to do work. That's chemical energy. It's found in foods and fuels. If you think about it like this, anything I burn is chemical energy. The propane locked up in this tank is chemical energy that I'm converting to other stuff. Food is a chemical energy because I'm going to eat it and digest it and break it down and get the energy from it. There's lots of sources of chemical energy out there. Thermal energy is energy due to temperature. An object at a higher temperature has more thermal energy than if it was at a lower temperature. And it depends also on the mass and material of the object, but generally thermal energy travels from a high energy area to a low energy area. That's why I can feel the heat coming off of my heater over here, even though it's a couple feet away, is because the high energy heat coming right off the burner is moving through the air towards me as it moves to the low energy system. There's no such thing as cold. There's no like cold energy. Your freezer doesn't add cold to your freezer. It just removes the heat. We'll talk more about that later. That one bothers me for some reason. So the last one is fluid pressure. Fluid pressure in gases and liquids creates a form of stored energy. You could imagine a bicycle tire. When you blow up a bicycle tire, the tire inflates and gets really big. And if you were to pop it, it would explode out and launch pieces. That's energy being used. I like to think of a balloon. You blow up a balloon and it inflates. And then when you let go of it, the balloon flies around the room as the air is forced out. Because there's a built-up pressure of all those molecules in there pounding on the balloon trying to get out, it's stored energy. If it was to be poked with a needle or something, it would explode as the air rushed out. So you can use that to store energy. Let's say you boil water and capture the steam. Well, now that steam is very densely packed in there, and it has a lot of pressure behind it. You can use it to do things like turn a motor so that we can generate electricity. So to recap, energy is the mediator of all physical changes. It's responsible for all physical changes, such as changes in speed, height, temperature, or chemical composition. We measure it in units called joules, and most importantly, energy can never be destroyed. It can only move from one of these sources to another. And that's what we're going to work on next time. So with that, I'll say goodnight and see you guys later.